Chapter 23, Section 2 is Faraday's law of induction and Lenz's law. Michael Faraday discovered this relationship between changing flux and induced EMF or induced voltage. And that's why the equation that you see here is named after him. This is Faraday's law of induction. It says that the EMF or the voltage produced in a loop of wire is proportional to the number of turns of that loop of wire. So if I have 3 loops, it'll get 3 times the effect as 1 loop. It's also proportional to the change in the flux. So this is an important part of this concept, is that it's the change in flux. It's not the flux, but it's the change in flux. And it's also dependent on how fast the flux is changing. The faster it changes, the larger the effect. So this is Faraday's law. EMF is minus N, change in flux over change in time. This quantifies the velocity that is produced when we have a changing flux, changing magnetic flux. The minus sign in particular is named after a Russian physicist named Lenz. Lenz's law is basically the minus sign in Faraday's law of induction. The minus sign means that the EMF that's produced is going to oppose the change of the flux. Now there's a number of steps involved to do this, and it's outlined here. So you have to go through these steps to figure out which way the induced voltage or the induced EMF is orienting, which way it's driving the current. So we'll walk through this process. First of all, draw the picture. We've got the picture already drawn for us over here. Step 2 is look at the direction of B. So you're figuring out what the direction of flux is. So in this picture, what we've got is a bar magnet. We've got the north pole oriented towards the right. We have magnetic field lines coming out of the north pole. We're going to take the magnet, and in the first picture, we're going to move the magnet to the right, and it will approach the coil of wire. So we've got a coil of wire here. The magnetic field is pointing to the right. So that's step 2, is determine the direction of the B field. The B field is pointing to the right. Step 3 is determine if the flux is increasing or decreasing. So first of all, the flux, the B field, is pointing to the right. Because the bar magnet is moving closer, I'm putting more magnetic field lines inside the loop, and so the flux is increasing. So B field is pointing to the right, and the flux is increasing. Lenz's law is you oppose that change. So step number 4 is you flip the direction. So if I'm increasing flux toward the right, then the loop will feel an induced voltage, an induced EMF, which opposes that change, meaning the loop creates its own magnetic field pointing to the left. And the way it does that is by having the current flow in the loops of the wire in this orientation. So on the side closer to me, it moves up, and on the side further away from me, it moves down. That's the direction the current flows due to the induced EMF. Now, walk through the steps one more time when I move this away. So now the bar magnet starts out close to the loop, and I slide it away from the loop. So step number 1, the picture's drawn for us. Step number 2, determine the direction of the B field. The B field is pointing to the right, so there is a flux going toward the right through the loops of wire. Step number 3 is the flux increasing or decreasing. Since I'm moving the magnet away from the wire, the flux is decreasing. So the B field's pointing toward the right, but the flux is decreasing. That means the loop of wire, step number 4, opposes that change, and so it will create its own B field opposing the change. Again, there's a magnetic field pointing towards the right, but it's getting smaller. And so the induced EMF will try and maintain that magnetic field that was there before. And so to do that, to create a magnetic field in that direction, right-hand rule tells me that the current will flow in the wire in this orientation. So the parts of the wire that are closer to me, it flows down. The parts that are farther away, it moves up. You can walk through the third one yourself as an exercise. But again, go through the steps, draw the picture, figure out which way the magnetic field is pointing, ask the question, is the flux increasing or decreasing? Then oppose that change. The loop will create its own magnetic field to oppose whatever you determined in step 3, and then use the right-hand rule to figure out what the direction of the current is due to that induced EMF. Let's take a look at that animation we had earlier and walk through this process. So here we have a bar magnet near a loop of wire, and in the first part of this process, the bar magnet is moving toward the loop of wire. So we go through the steps. We've got a picture drawn. We look at the direction of the B field. The B field, because the north pole of the bar magnet is near the coil of wire, the magnetic field lines are pointing up. So there's a flux going up through the coil of wire. As I move the bar magnet toward the coil of wire, I'm increasing the flux. I'm adding flux to the wire because the magnetic field is getting stronger. The loop of wire will want to oppose that, and it will create its own magnetic field pointing in the opposite direction, pointing down. The way it does that is it creates a current flowing in this orientation so that it creates a magnetic field opposing the change in flux. Now, if I look at the case where the bar magnet is moving, the north pole of the bar magnet is moving away from the coil of wire, walk through the steps again. I've got the picture drawn. The magnetic field is pointing up through the loop, but the magnetic field strength is decreasing. The flux is decreasing because I'm pulling the bar magnet away. So the flux is decreasing. That means the loop will want to increase the flux. It will want to create its own magnetic field pointing up. And the way it does that is by current flowing in this orientation.